at creep events along the San Andreas Fault. So as Tamara also mentioned, this work has recently been published. So if this piques your interest in looking at creep events, feel free to go and check this out. I'm going to go through some of this work with you today. So as we know, or as I'm assuming we know, there's lots of faults all over the world that have been observed to slip aseismically. And some of these faults have slip that occurs at a steady rate, and some of them have slip that may occur in bursts. And one of these faults, which I'm going to focus on today, is the San Andreas Fault. So the creeping section of the San Andreas Fault runs from San Juan Bautista to Chile. It's about a 175 kilometer long section that was noticed to creep at the surface in about the 1960s. Either end of this creeping section is bound by a locked section, which is over 100 kilometers long. This locked section to the north last ruptured in the 1906 magnitude 7.9 San Francisco earthquake and the 1989 magnitude 6.9 in Loma Prieta earthquake. And the locked section to the south last ruptured in the 1857 magnitude 7.9 Fort Hood earthquake. None of these large earthquakes ruptured into this creeping section, but there are smaller earthquakes that do occur along the kind of towards the edge of these creeping sections, particularly around Parkfield, where there's a repeating sequence of magnitude 6 earthquakes, but there's been no magnitude 7 or above earthquakes reported on this section. So the majority of the slip along this creeping section is seismic. So after creep was discovered in the 1960s, the San Andreas Fault was heavily instrumented with creep meters, strain meters, GPS, alignment arrays, you name it, that instrument is probably on the San Andreas monitoring creep somewhere. And what these instruments allowed us to do was notice that creep wasn't occurring at just a steady rate, but rather it was occurring at a steady rate that was punctuated regularly by bursts of slip. And these bursts of slip are typically a few millimeters, they last a few hours to days, they recur every few weeks to months, and these bursts of slip are known as creep events. So here on the right, I have two examples of creep events at two different places, one at Cienega Winery and one at Middle Mountain. And you can see that they do not necessarily look the same. So this shows us a wide variety of creep event behavior. So despite the fact we have these creep events known about since the 1960s, we still do not know how spatially large they are, like how long they are along strike, how long they are along depth, or the fault zone processes that kind of drive these. And it's important to understand the roles of these events, as they may play a key role in understanding the physics of creeping faults, and they may have wider implications for understanding fault physics in general, which can then feed into things like seismic hazard. So today I'm going to discuss about how long creep events are, and there's kind of these three previous scenarios of how large creep events are. So there's these possibilities that they're small, 100 meter long, 100 meter deep slip occurring in these creep events, or you might have creep events that are a few kilometers long and like up to a kilometer deep, or you might have these large kilometer long, kilometer deep creep events. So yes, we can have these three scenarios, but how do we actually look at creep events? How do we like monitor them? So there's these instruments called creep meters, which were installed in the 1960s along the San Andreas Fault. Here is a diagram of one up at the top here. You've got two piers which are driven to as far as they can be driven in, and then there is a rod that stretches between the two piers that crosses the fault at an oblique angle. And as the fault slips, as you can see in this GIF down here, this rod is moved or extended, and then you use this extension to then, and the angle that you've installed the creep meter at, to then work out for fault parallel displacement. So these creep meters currently have a sampling frequency of about 10 minutes, and they have sub-millimeter accuracy. And since they were installed in the 1960s, and some of them are still running today, they're one of the longest continually running monitoring instruments of fault creeps that we have as a community. So to use these creep meter data to find creep events, and before you even think about how big they are, you need to know when they occur. So to do this, you can do it manually, but it's very time consuming. So instead, what we did was we took a template creep event for each creep meter and did a cross correlation to identify times of similarity to the template that also had a significant amount of slip. And we did this for all of the available 18 USGS creep meters. And doing this, we were able to identify 2,120 creep events. So here's some nice bar charts showing us the kind of some basic statistics, like the number of events, the amount of slip, the duration, or the percentage of slip that is occurring in these events compared to the total amount of slip. And there's kind of three main things that we can take away. So here at XSJ, we have a few events, but they're quite large. They have 3 or more millimeters slip on average. They average last more than 2 days. Or on the other end of the spectrum, we have somewhere like XMM, where we have over 500 events, but all of them are normally under 1 millimeter, and they last for only a few hours. So you've got these like two kind of end members of how your creep event can accommodate slip. But what we notice about most of these creep meters is that most of these creep events are accommodating 50% of the slip observed at the surface at most creep meters. Unfortunately, some of these creep meters have quite low percentages because the instrument has got left lateral slip on it instead of the normal right lateral slip, so it makes working out the percentage of slip difficult. So great, we've got this catalog of creep events now, but now we need to work out how long they are. So the way we do this is you can compare the timing of creep events to each other to try and work out how big they are. So we have this example creep event here at Cienega Winery on May the 23rd. And then if we go to the next creep meter up, which is 4 kilometers lost, we have the creep event again at Harris Ranch. So if you look within 24 hours either side of your starting creep event, you can then see how these creep events are related to each other, whether you've got one within 24 hours or you haven't. The reason we looked in a 24-hour window was because if you look in a window shorter than 24 hours, you can lose some of the slowest propagating creep events. But if you look in a window longer than 24 hours, it then gets complicated with having multiple detections correlating. So you can't determine whether you've got one creep event that's correlating and one that isn't, or whether you've got 3 unrelated creep events. And then, so we've got these pair of creep meters that both have creep events at similar times. They're 4 kilometers away, so we have this creep event that might be 4 kilometers long. So next we go to the next nearest creep meter, which is at San Juan Bautista, which is 11 kilometers further north again. And here you can see if we search within 24 hours, we are unable to find a creep event. So you can do this manually. You can go through the creep event catalog and compare them, or you can do it in a slightly more robust statistical framework. So here, what we did is for example, we have an original time series of creep events at 1 creep meter, where we have grouped all the creep events into years. And then what we do is we randomly select these years with replacement to create a bootstrapped time series. And this bootstrapped time series is then compared to the original time series at other creep meters to work out what is the likelihood if I have an event at CWN, say, that we're also going to see it at XHR. And that's what this figure here is showing. We have 2 examples plotted, one for CWN XHR and one for CWN XSJ. And initially looking at this, you could say that CWN and XHR look like they're related, so that orange graph, whereas the CWN XSJ graph looks like there might be a slight relation, but it's not as clear as the CWN. However, there's a possibility that these events could just be correlating by chance. So in order to account for whether these creep events are occurring by chance, we do a shifted time series where we take the original time series and we shift it by multiples of years. So we take it, so all the events that happened in 2001 now happen in 2002, and all the events that happened in 2010 now happen in 2001. So we loop it back around so we have the same amount of time. And then we repeat the comparisons between the shifted timescale and the original timescale to come up with a by chance distribution. This shifted timescale also accounts for seasonal variations, because there is long-term seasonal variations where creep events might like to happen more in winter. And by shifting in multiples of years, you can keep that seasonality. You can account for that seasonality. So we have this distribution of observed creep events. We also have this distribution of by chance creep events. So if we want to know how many creep events we're actually observing, we need to subtract this by chance distribution away from our bootstrap distribution, which gives you this real distribution that we have at the bottom. And with this real distribution at the bottom, we can see that the green curve of CWN XSJ appears to be unrelated because they center around 0, and if they center around 0, the relation, if they do 2 events that happen at the same time, it most likely is happening by chance. However, the CWN XHR events hover around 25, which means that if there's coincident times between the two, it's likely that they could be related to each other. So doing this for all the creepmeter pairs, all 18 creepmeters with every other creepmeter, it's possible to come up with 306 possible long multi-creepmeter events. And these events can be categorized into like 5 categories, from isolated events, short, medium, and large, and then possible multi-strand creep events. So I'll start off with these isolated events. These typically tend to be creepmeters that are far away from each other. So for example, this green XMR here, it's 23 kilometers further south than its nearest neighbor to the north, and it's 70 kilometers further north than its nearest neighbor to the south. So there could be creep events that could be several kilometers long here, but unfortunately, due to the heterogeneity of the instruments, we're unable to tell whether this creepmeter has a relation with any other creepmeter. XSJ, for example, as we showed earlier with XHR and CWN, it's just too far away to have that relation with those creep events. So the creep events here could be propagating between these 2 creepmeters, but not extending far enough to get to the final one. The interesting pair of these isolated creepmeters is down here at CRR and XGH, so Car Ranch and Gold Hill. These 2 creepmeters are only 1 kilometer away from each other. However, they don't have creep events to communicate with each other. One will slip in a creep event, or will be slipping, and the other one will be stationary, and then vice versa. The other one will slip, and the other one will cease to slip. So then the first category of creep events to have multi-creepmeters is these small, these are less than 2 kilometer events, and they typically happen around the XMM, XMD, so this middle mountain area, and also at C46, X46 down in Highway 46. So these are typically, these events typically happen together. So you have about 10% to 20% of XMM events being observed at XMD, or in the Highway 46 case, you've got 50 or 60% of creep events observed at one creepmeter are occurring at the other. So then we have these medium-sized events, these 3 to 6 kilometer events. So we have this creepmeter pair up at XHR and CWN again, where you have over 20% relation between these 2. So if you have a creep event at XHR, 20% of the time you'll have a creep event at CWN. But then we also come back down to this middle mountain region with XMM and XMD, but occasionally them 2 just slip together as a pair, or occasionally they include their friend at XVA further down. And then you have all 3 creepmeters slipping in a sequential creep event that moves down through the creepmeters. XVA also, as well as slipping with the creepmeters to the north, sometimes slips with the creepmeters to the south at XPK and XTA. And here again is an example of a creep event at those ones. And then you can see that the percentage of creep events observed at XVA is high for XPK and XTA, which are these 2 points here. So then it's possible, we do occasionally see large events. These events are 10 kilometers or more. We have if you have the 2 sections from XMM to XVA and XVA to XTA, down here in these 5 colored triangles here, it's possible, we occasionally see creep events that rupture both of those 2 5-kilometer sections. So both those sections go together in one creep event that propagates all the way through those 5 creepmeters. There's also a relation between XSC, which is this triangle here, and WKR, which is the one down at the bottom of this black rectangle here. And as you can see over here, there's quite a strong relation between these 2 creepmeters, and these 2 creepmeters are like 31 kilometers away from each other. So if we're just looking at this as is, and we don't take into account any other factors, then we could say that there is a potential 31 kilometer creep event here. However, the elephant in, getting ahead of myself. There's also these evidence of some multi-strand ruptures in these. So down in the Parkfield area, there is the main trace of the San Andreas and also a southwest trace just below it. And it is possible for creep events to be occurring on this southwest trace itself. So here's an example of one of these bursts of slip on this southwest trace. but also a relation between events on the southwest trace and the main San Andreas Fault. So these are the percentages of creep events at XHSW, and you can see that there is a relation with creep events that are on the main San Andreas Fault. So this red, yellow, blue points here. So it's possible you have all these 5 different behaviors, but the thing about with creep events is the creep meters are only buried at up to 1 meter depth. So it's possible that you could be having an influence from rainfall. So in order to identify whether these long events are tectonically driven or whether there's coincident events because you've had a rainstorm moving through, we repeated the analysis. And instead of comparing the original time series to everything, we removed events that had rain in the 3, 7, and 14 days beforehand. These range of timescales for removing rain are fairly arbitrary. However, they do allow for a variation in the timescale for water infiltration into the soil, because as we don't know the depth of these events, we don't know how far down this rainfall has to percolate to have an influence on these creep events. And this allows for an interpretation of the frequency of multi-creep meter events in the light of rainfall. So you kind of get these 3 different behaviors. So you have these creep events that are affected by rainfall, some that aren't affected by rainfall, and somewhere if you remove the rainfall events, the percentage of creep events actually goes up. So the events that are typically affected by rainfall, these long, really long events. So it looks like that when you remove the rainfall from that XSC WKR pair, that when you remove rainfall on timescales of 7 days or 14 days, the relation between these 2 creep events disappears. So it looks like these very, very long, like 31 kilometer events are driven by rainfall. So they're rainfall related and they're not due to a tectonically driven creep event. You also have these, the vast majority of pairs of creep meters or threes of creep meters are unaffected by rainfall, whereby when you remove the rainfall events, the percentages just don't change. So some of these events that might have been correlated might have been driven by rainfall, but again, the vast majority look to be very unaffected by them. And finally, if you remove the rainfall from the CWN-XHR pair, the percentage of creep events increases. So this could be suggesting that we have small, shallow creep events that are triggered by rainfall at individual creep meters, and then these multi-creep meter events are longer, deeper, and driven by slip at some depth below the surface. So the wider kind of implications of this is that if we've decided that we have creep events that are several kilometers long, but we don't necessarily know how deep they are, but we know that creep events are accommodating up at 50% of the slip at the surface in most places, well then you could start on the line of thinking of how much of this slip is being accommodated in these creep events to a certain depth, and how does this work with the overall driving physics of the entire system. So that's kind of where our thinking is going. So we're going to hopefully start to work out the depth of these events and then try and amalgamate all this in together to try and get a driving understanding of how these creep events are occurring and how they're accommodating slip on this creeping section of the San Andreas Fault. So to sum up what we've done in this study so far is we've identified 2,120 creep events on 18 USGS meters between 1985 and 2020. This led to 306 possible multi-creep meter events, which span various lengths along strike, and the vast majority of these events are not correlated with rainfall. So this lack of correlation with rainfall suggests that rain isn't driving these events, therefore there must be something else driving them. But in order to better understand that physical process, we need to determine the depth of these creep events, which is something we are actively working on now. So if you have any questions, you can put them in the chat or the Q&A, or if you want to email me or contact me on Twitter, my contact details are here. And as I mentioned at the beginning, if you want to find out more about this work we've been doing, you can check out this paper in JGR Solid Earth. I would also like to draw attention to the fact that in this paper, we have included freely available the catalogue of creep events for people to use and to look at. And if they're of any use to you, please feel free to use those catalogues in your own work. Thank you for listening, and I will hand back to Tamara.
We have 2 questions for Dan currently, so we'll get started on those in a second. But yes, feel free to throw Sophie any questions that have come up, and we'll also go back and forth between our speakers. So going back to Dan's talk, and if you have any questions for Dan, feel free to put them in the chat. Let me just get the chat box open. So Athanasios Garnas has asked, is there a relation between rainfall intensity and amount of creep, or all creep events are similar in size?
So it kind of appears that creep events, whether there's rainfall beforehand or rainfall not beforehand, they kind of appear to be a similar sort of size at each creep meter. So each creep meter tends to have a similar sort of size of creep event. And it doesn't really change with the amount of rainfall or whether there's rainfall or not. You just kind of get, if you're looking at, for example, CWN, you typically get a 1 to 2 millimeter creep event, and that doesn't change whether it's rained or not.
Yeah, cool. Hopefully that answers your question, Athanias. Sorry, apologies for pronunciation. Susan Schwartz has asked, is there a relationship between slip length and slip amplitude? Also, have you looked at the creep events with a 10-minute time increment? She's wondering if some of the motion that appears as creep over longer time may occur as stick slip. So have you correlated any of the slip events with the seismicity catalogue?
So the relationship between slip length and slip amplitude doesn't appear very obvious. So it's kind of when you plot the slip length against the slip amplitude, you tend to get a very large peak at small slip amplitudes, but this is typically the pair. This is typically the data points from the pair of C46, 846 down Highway 46, which typically has larger creep events than the rest of the creeping section anyway, even when they're not correlated with each other. So the rest of it kind of then settles down, and they kind of all a similar slip amplitude, regardless of the length that they're slipping to. So with regards to the 10-minute time increments, so when we do the correlations between the events, we're looking at the 10-minute sampling of the creep meter data, and some of the creep events appear to be very smooth curves as they creep, and some of them do appear to be slightly more steppy, a way of putting it. So it kind of has these steps between the data points, but this could just be the fact the instrument has been there since 1960. So it's probably degraded a little bit. Recently, Roger Billam has installed an upgrade to some of the creep meters to look at 1-minute sampling, and sometimes some of these steps appear to smooth out when you have a more densely sampled creep event. With regards to the seismicity catalogue, this is something we're going to move forward, because hopefully we're going to be looking at the depth. So if you want to look at the depth, then it might make sense to then look at the seismicity catalogue and look at the repeating earthquake catalogues as well, to try and see if there's some relation between these repeating earthquakes at depth and also then these creep events at the surface, and then try and correlate them that way. So it's something we're working on, but it's not something I have actually a solid result on at this very moment in time.
Cool, thank you, Susan. I hope that answers your questions. Put any follow-ups back in the Q&A box. Question that's come in for Dan. So Dan, do you measure creep across one fault or multiple fault planes?
So the creep meters are typically somewhere between 10 and 30 meters long. So they kind of, in a lot of places, they only cross the main San Andreas Fault plane, so that one fault. Occasionally, if the San Andreas has multiple cracks at the surface, it might cover all 3 or 4 of those cracks. But this kind of means that you're not getting any of the distributed deformation away from the fault. You're just measuring what is happening on that fault plane where the creep meter is. It's why creep meter slip rates are always lower than the creep slip rates you get from INSAR or GPS, for example, because you can sample a broader aperture of the slip, whereas these creep meters are just on that one or two strands that are within that 10, 20, 30 meters.
I have a quick follow-up to that, actually, if we don't have any current unanswered questions. I wonder if the broader slip being measured by INSAR or GPS measurements or something like that, does that give you any insights to sort of, does slip accumulate? Can you see slip accumulating in those methods, and then these creep events happening to release that? Or is there any sort of, I guess the answer is there any correlation between those two amounts of slip?
So the general amount of slip in the INSAR is generally higher because you're measuring obviously the distributed deformation of the fault as well. With the problem with the INSAR is the INSAR, obviously it comes around every 12 days, and because these creep events are millimeters, sometimes sub-millimeter amounts of slip, so the INSAR can't actually detect them until there's a significant amount of them that has happened, and you've got enough INSAR images through that you can then get the next. So you've accumulated enough slip in these creep events to then have them appear on the next image at some point down the line. So that's the problem with using INSAR or even GPS to try and identify these creep events, is they're just not sensitive enough to the size of the creep events. So to look at the creep events in the INSAR, you'd have to stack it in a certain way to boost the signal, so you could actually find the amount of slip occurring in these creep events from INSAR.
Yeah, cool. That makes sense. Cool. There's a comment saying with INSAR you measure up, down, and east, west, but the San Andreas Fault is orientated north, west, southeast. So you'd need to tie to a GNSS station. Thank you. Yeah, that sounds that sounds fair. Yeah. Cool. Well, we don't have any other questions in, and we're just about right on time. So I think that was wonderful. I think I will call it there and thank both of our speakers. Thank you so much, Sophie and Dan, for agreeing to give these talks and giving these wonderful talks. I hope that the audience has taken something away from them, and thank you so much for coming to support our COMET webinars and particularly our COMET students today.